Hello, everyone. My name is Jianhui Wan, and I am an AI research engineer here at Espressif. And our AI team works on a couple of speech-related projects, from speech enhancement, speech denoising, speech recognition, and etc. And today, I'm going to give you a talk on our customizable speech command recognition system that is currently supported by ESP32 X-ray series boards. And I hope by the end of this talk, you will have a general idea of how our system works, how to use it, and how to customize it for your own needs. Here is a chart of our entire pipeline. So the input to our speech recognition, speech command recognition system could be either directly from a microphone or from some pre-recorded audio files. And the input audio will first go through a audio front-end component. The audio front-end component has a few algorithms that applies audio enhancement to the input audio signal. And the enhanced audio will then be fed into our wake word engine we call WakeNet. The wake word engine is always listening until a wake word is detected. And once the target wake word is detected, the wake word engine will go to a standby mode and our speech command recognition model will be active. The speech command recognition model will listen to the audio after the wake word, and once a predefined speech command is detected, it will output the corresponding speech command. Currently, we support both Mandarin and English speech command recognition model, but only one model can be active at once. They can be switched or selected before you flash the program onto the board, and I will give a tour on how to do model selection in a small demo later. The detected speech command ID, there is an option to speak out this command via a speech synthesis system, a TTS model. Currently, only the Mandarin TTS model is supported and the English model is under development. The detected speech command can then be sent to any post-processing as you like, such as to control your smart home appliances from your music speaker to air conditioner. To sum up, in order to perform speech command recognition, a wake word must be spoken first. And once the wake word is detected, you can speak as many speech commands as you like until there is a period of silence that is long enough to trigger a predefined timeout. The predefined timeout is normally set to 5 seconds to 6 seconds, depends on the use case. So as shown on this graph, WakeNet will be actively listening until high ESP is spoken. Once it detected high ESP, WakeNet will go to a standby mode, and Multinet will be active. Multinet will be able to output the speech command ID from a series of speech commands: increase the temperature, turn on the lights, turn off my soundbox. And once there is silence that is long enough to trigger the timeout, Multinet will be disabled and WakeNet will be active again. Next, I will introduce each component in our system individually. The first component is the audio front-end, AFE component. Here is the workflow of our AFE component. Since the speech command recognition system is normally used in an indoor environment where exists a lot of room echoes or reverberations, therefore the first component is the acoustic echo cancellation component. The audio input first goes through the acoustic echo cancellation system, followed by a noise reduction system. The noise reduction system performs either blind source separation or noise suppression, depends on the microphones that are being used. Blind source separation is used in the case of dual mic, and noise suppression is used in the case of single mic. The last component of AFE is voice activity detection filters out part of the audio that does not contain active speech. And the filtered audio is then fed into our WakeNet. Of course, if you are using this system in an environment where exists almost no background noise or room echoes, you always have this option to bypass all these components to get a further speed up. The second component in our system is the wake word engine, WakeNet 9. Weak word engine is a crucial part in our system as it tells the speech command recognition model when to start listening. WeakNet 9 is built upon a neural network structure and it supports up to 5 weak words at the same time. We first extract audio features from the input audio. The audio features that we're using is called male frequency capture coefficients, MFC. It's the type of feature that is specifically designed to model how human ears perceive speech signals. That is, to put more attention on the lower frequencies and less attention on the higher frequencies, just like how human ears work. The extracted MFCCs is then sent to the neural network, and the neural network acts like a classifier that classifies the input features into wanted word class or unknown word class. The unknown word class may contain other words or just any kind of background noise. In the case of multiple weak words, let's say, for example, 5 weak words, the neural network works like a multi-class classifier that classifies the input features into 6 classes, 5 wanted words, and an unknown word class. More specifically, WeakNet 9 uses a dilated convolution model structure. It is a rather small model with less than 300K parameters, and the average running time for a 32 millisecond frame is 3 milliseconds. The reason that it is measured of 32 milliseconds is because WeakNet 9 produces one classified result every 32 milliseconds. And during runtime, it uses the average results over a few frames to get a final reliable results. This table shows the detection accuracy of WeakNet 9 on Alexa dataset at a false alarm rate 1 at 12 hours. In other words, this model is false triggered once every 12 hours. The first column here, distance, is the distance between the audio board, the audio source and the board. And when the board is 1 meter away from the audio source, WeakNet 9 is able to achieve 98% accuracy in a quiet environment. And if we add additional stationary noise to the audio source at an SNR of 4 dB, the WeakNet 9 is able to achieve 96% accuracy. And if we add additional speech noise at an SNR of 4 dB, WeakNet 9 is able to achieve 94% accuracy. If we move the board further away from the audio source from 1 meter to 3 meters, the performance of WeakNet 9 is not affected. The third component of our system is the speech command recognition module, MultiNet 6. It is activated once a weak word is detected, and it outputs the command ID when a speech command is spoken. Here is the workflow of our speech command recognition module. It consists of 2 major branches. Let's look at the upper part of this graph first. Similar to WeakNet 9, we are extracting MFCC features from the input audio, and the extracted features is then sent to a neural network. We're using a conformer-based neural network structure for MultiNet 6. I will add more details about this model structure in a few slides. Now let's look at the lower part of this graph. In the blue box is a list of predefined speech commands with their corresponding command IDs. For example, we have command ID 1 associated with the sentence turn on the lights, and the command ID 2 associated with the command decrease the temperature. This list was then sent to a command FST. FST is the abbreviation for finite state transducer. I will add more details about this structure in a few slides as well. It is okay for multiple commands to have the same command ID in the predefined command list. For example, we can have decrease the temperature is too hot and make it cooler in the command list, and they can all have the same command ID too. During runtime, you can speak any of these 3 sentences and the system will be able to output command ID 2. This feature gives you the flexibility to use different phrases to convey the same intent. The output of command FST works jointly with the output of Multinet 6 to get the final results, whether there is a command, a predefined command in the input audio or not. Now I will touch on the model structure of Multinet 6 and finite state transducer briefly without being too technical. The model structure of Multinet 6 conformer is shown on the left. It is a very popular used neural network structure nowadays in speech recognition tasks. It uses a combination of feed-forward layers, convolution layers, and multi-head self-attention layers. And it is able to achieve the state-of-the-art performance in speech recognition tasks. On the right is the finite state transducer that is built upon a list of 4 commands. Command 1, turn on the light, command 2, turn off the light, command 3, decrease the temperature, and command 4, increase the temperature. The resulting finite state transducer has 7 states here in circles. And the arrows means that we can travel from one state to another. State 0 is the starting state, meaning that we can travel to any state from here. And state 6 is the final state, meaning that we have successfully decoded one command that is represented by a path. We will use the first command, turn on the light, as an example. As highlighted in orange here, we can travel along the path from state 0 to state 1 to state 2 to state 3 to state 6 to finish this command, turn on the light. And note that we also have the second command, turn off the light here. So when the speech recognition model outputs the first token turn, there are 2 possible commands, turn on the light or turn off the light. And once the speech recognition model outputs the second word on, the only possible command is turn on the light with the command ID 1 here. So the FST works jointly with the output from speech recognition model to constrain the output of a speech recognition. In other words, we are actually limiting the searching space of speech recognition model to those predefined commands. So the entire system will output either a command ID or nothing. This FST can get a lot more complicated if there are tens or hundreds commands in the command list, but the idea behind it stays the same. Multinet 6 has around 3.8 million parameters, and the average running time per 32 millisecond frame is 12 milliseconds. Here in the table is the word error rate of Multinet 6 compared to our previous version of Multinet 5 on 2 open source datasets, LibreSpeech and AIShare. LibreSpeech is an English dataset that contains reading audiobooks, and AIShare is a Mandarin reading dataset. Word error rate here is the commonly used evaluation metrics that in recognition task. It is the summation of word insertion, word deletion, and word substitution. Since it is an error rate, the lower the better. The -en and -cn here represents the English model and Mandarin model, respectively. And as we can see from this table, Multinet 6 is able to outperform Multinet 5 by 7.5% in LibreSpeech and 4.3% on AIShare. This table gives the speech command recognition rate on our internal dataset. Multinet 6en is able to achieve 96.8% recognition rate in a quiet environment. And if we add additional stationary noise, it is able to achieve 87.9% recognition rate and 85.5% recognition rate with additional speech noise added. The Mandarin model shows a similar behavior. It achieves 98.8% accuracy in a quiet environment and 88.3% accuracy with stationary noise added and 88% accuracy when speech noise is added. Besides these two models, we also released a memory model that is specifically targeted at air conditioner commands. We name it Multinet 6-EN-AC here on the last row. Although it has like 1.7% recognition rate lower than Multinet 6-CN, it is able to achieve 95.1% and 96.8% recognition rate when additional noise is added. Our team is currently working on the next generation of Multinet, Multinet 7. It has not been released yet, but I will give you a peek into our progress so far. The general workflow of Multinet 7 stays almost the same as Multinet 6. The major difference here is that we are changing the conformer-based model structure into a newer one called ZipFormer. I won't go to details about the model structure today. If you're interested, you can look up the references, or we will publish a detailed documentation once the Multinet 7 is ready and released. Here is the performance of the English Multinet 7 compared to the previous version on our internal test set. It is able to outperform Multinet 6 by 1% in a quiet environment and 1.5% with additional stationary noise added, and 2.6% higher than Multinet 6 when additional speech noise is added. Moreover, it has 1 million less parameters than Multinet 6, which means that it consumes much less memory and runs faster on board. This is an experimental result, and we are currently working on testing the model, finalizing it, as well as building the Mandarin one. With all those technical stuff being said, next I will show you a small demo on how to use this system on ESP box using WakeNet 9 and Multinet 6. We have a few working examples published on our open source repo ESP Skynet, from weak word detection to speech command recognition. And in order to run those commands on ESP Skynet, you will need a few things first. First is an audio development board that comes from the ESP32S3 series. We recommend you to use Quavo 1 or Quavo 2 for best experience. The second is a USB cable that works with the board. It could be a Type-C cable or micro USB cable, depends on the board you are using. And the third is a PC that runs Linux for development. On the software side, you will need to clone the latest ESP Skynet repo, which also uses ESP-SR as a component. You do not need to download ESP-SR separately, as it is already included in ESP Skynet. You will also need to install the ESP IDF and make sure that it is the correct version that is recommended in ESP Skynet. Next, I will show you a demo that runs on ESP box. It is basically the same as the example in ESP Skynet, with some additional screen display to give you a better visualization. The first step is configuration and flash the program onto the board. I'm sure that you are pretty familiar with this process if you have worked with any ESP project before. So first, we're going to set the target to ESP32S3. And next, we will need to use menu config to select the models we want to use. Today, we are going to use the English Multinet 6. Once the configuration is saved, we can now flash the program onto the board by using idf.py flash. If this is the first time you are building this project, it might take some time for the program to build. So I'm going to skip this today. Now let's look at how it looks on the ESP box. Hi, ESP. Turn on the light. Increase the temperature. Turn on my soundbox. As we can see from the video, the system is able to pick up a series of speech commands once high ESP is detected. And if we don't say anything for a while, it will go to standby mode and waiting to be woke up again. Next, I will show you how to add some new commands as well as modify the existing commands. You will be able to find this piece of code in our ESP Skynet example. This is basically how we build a multinet. To add a new command, we will use the function espmn commands add. The first input argument is the command ID, and the second input argument is the command sentence. Here we are adding two new sentences, command 50, turn on the kitchen light, and command 51, shuffle my playlist. We also want to change the existing command by using espmn commands modify. We're changing turn on my soundbox into turn on my speaker. And at last, we're going to use espmn commands update to apply all these changes we just made. After reflashing the program onto the board, we can now test how it works. Hi, ESP. Turn on the kitchen light. Shuffle my playlist. Turn on my speaker. Turn on my soundbox. We can see that the model is now able to pick up the two new speech commands that we just added. And since we changed turn on my soundbox into turn on my speaker, it can no longer detect turn on my soundbox anymore. I encourage anyone that is interested in this project to try out our examples on ESP Skynet. And if you encounter any problems along the way, please feel free to contact us and we are willing to help. At last, I'd like to share with you the next steps of this project. In the near future, our team will be mainly working on two things. The first thing is that we're aware that there are a lot of needs of using customized wake words other than just high ESP or high latency. Right now, we need around 20K pre-recorded wake word sentences to train a new wake word model. And this is both like time consuming and budget consuming. So we are looking at alternatives to reduce the burden of manual data collection. And the text-to-speech engines nowadays is capable of produce natural human-like speech with a diverse collection of speech voice. Therefore, we are planning to utilize such a TTS engine to reduce the amount of real data required. The second thing that we're going to work on is Multinet 7, as I shown before. Both the English version and the Mandarin version will be released soon, so stay tuned. Here is a list of references for this presentation that you might find helpful. And please ask questions if you have any.